During these notes, we're going to focus on Q and W. Q and W are basically heat and work. So when we talk about heat and work, the main thing to recognize is they're simply energy, the ability to cause change. The one thing I want you to remember most about heat is not equal to temperature. In fact, we know that temperature is average kinetic energy. So we know that they are related, but they are not directly the same thing. What matters most about heat as opposed to temperature is heat flows, temperature doesn't. Now, the second thing, and the main reason we care about this, is the first law of thermodynamics. First law of thermodynamics basically states that energy cannot be created or destroyed, but it can be converted. We can transfer energy from a system to surroundings. Now, why this matters is the energy of a system, what's known as the internal energy. Now, the internal energy is the sum of all the potential energy and kinetic energy. So since it's the sum of all the potential energy and the kinetic energy, that means if I have work or heat flowing in or out, my delta E changes. So when we look at this, that means my delta E is the result of work and heat, and the direction of flow determines this. So when energy flows into the system, my delta E becomes positive. When energy flows out of the system, my delta E becomes negative. That means the values of Q, W, and E matter in terms of what we have come to be associated with endothermic or exothermic, or what are known as endergonic or exergonic reactions or situations. So we're going to start with work. In order to understand work in terms of pressure volume, or what we see with pistons, you have to have a change in volume. If my delta V is 0, then no work was done. Energy in the form of heat might have been transferred, but no work is transferred. That means the system doesn't do work and no work is done on the system. Again, we have to see that net change in the form of P delta V. We have to have a change in volume to see work done. So if you look at figure 5.4 in your book, which is much prettier than mine here, and something happens inside our system such that this piston is forced up, like what we see happen in a car, then my delta V becomes greater than 0. So we'll say it's, it doubles in size. Well, if that's the case, our equation, W equals negative P delta V, my delta V becomes positive. That means because of this negative sign, if the system does work on the surroundings, work was transferred out. It did work on the surroundings. Energy was transferred to the surroundings, so I have a negative W. If we go back to our energy equation, we know energy is Q plus W, and that means if we have negative W, that our E, our delta E here, has become negative. Delta E, because my W is negative. Work was done on the system. The direction of flow matters. Conversely, if the surroundings does work on the system such that I come down and my piston drops, now my delta V is a negative number. So in our original equation, since it's W negative P delta V, if this is a negative number, that makes my work positive value, and now my delta E is positive. And this is because energy flowed into the system. This is very different from when we look at Q. Let me back up. It's not different, you just have to remember the difference between the work and the heat. If heat flows in, okay, then my Q is positive, my delta E is positive because energy flowed in. If Q is negative, then my delta E is negative, and that means that energy flowed out. Where we traditionally see a lot of information with Q is when we deal with calorimetry. Now, I'm sure you remember calorimetry. Basically, recognize our equation here. We have Q equals ms delta T. It's based on heat capacity and or specific heat. If we know the actual mass, then it's specific heat. If we don't know the mass, it's heat capacity. And this you can see by the units involved in the when you're talking about heat capacity versus specific heat. And the difference is simply the presence of the gram. When we deal with specific heat, it's joules per gram degree. When we deal with heat capacity, it's just joules per degree. Now remember, one of the primary purposes of calorimetry, whether we're dealing with the bomb calorimetry or calorimetry like this, is we're simply looking at the transfer of heat. We want to see heat flow. Heat flow is everything, because heat flow tells us about and is a result of the nature of the substances. Not everything has the same specific heat. Not everything will change temperature by the same degree with the same amount of energy. And that's what's going on. It depends on the mass, it depends on the substance, the resulting change in temperature. All of that goes into determining or looking at how much energy is transferred. Now what we want to go back to is our first law of thermodynamics. We know if heat flows, that means something gained and something lost energy. The amount of energy has to be the same. It has to be equal. So when you look at something that is traditionally done, where you have, let's say you take a piece of hot metal, what you remember the lab. You put the piece of hot metal in the liquid. You looked at the change in temperature of the water and the change in temperature of the metal. You had known masses, and you could plug everything into the equation to actually solve for the amount of energy transferred and or to determine the specific heat of the metal. And that's usually what this lab was done. So if it equaled specific heat mass delta T, that means Q equals negative Q. I could set it up to do the same thing. So my water was, I plugged in everything I knew about water, CPM delta T equaling negative CPM delta T. And I gave the metal the negative because usually it was hotter going into colder water, so that meant the energy flowed from the metal into the water. So my water gained energy, my metal lost energy. You plug this in, you could solve for CPM delta T. Again, this matters simply because you want to be able to calculate what's going on with the change in temperature corresponding to a change in energy.